Hi, I'm Brad Clement. I'm going to talk about artificial intelligence for space applications. I work for the NASA Jet Propulsion Laboratory. JPL is a lead U.S. center for robotic space exploration and has space-based programs in the earth sciences and astronomy. JPL spacecraft have visited every planet of the solar system. This is an aerial view of JPL.
You can visit JPL's mission control room, where you can see missions uploading commands to their spacecraft using the Deep Space Network. You can also go to the Mars yard and try to scare the rover with loud noises.
So why would a space mission want automated planning? There are several reasons. Spacecraft are complex and expensive. Part of that expense is rocket fuel for the launch. The bigger the spacecraft, the more rocket fuel. So cost limits mass. Well, mass limits power because of the size of the solar arrays. And if you limit power, you limit communication signal strength, which restricts bandwidth. And bandwidth is a critical resource for a spacecraft because oftentimes they collect data a lot more quickly than they can send it back to Earth. So these limitations and the complexity of the spacecraft subsystems are captured in many rules and constraints for operating the spacecraft safely. This complexity can be overwhelming for science and operations staff. Thus, operations are also expensive. And spacecraft have a limited lifetime, so inefficient use of the spacecraft can reduce the value of the entire mission. Also, mistakes can be disastrous. Automation promises to reduce the complexity of operation, avoid human error, thus reducing mission cost and risk. That's not the only reason for planning. For a space mission, everything needs to be thought out in advance because once a spacecraft is launched, you can't replace a battery or add more memory. In addition, communication signals can take minutes to hours to reach the spacecraft, and communication is not always available. So the spacecraft needs to be able to receive a batch of commands and be able to operate on its own. You can't joystick the spacecraft. This requires predicting what's going to happen. Well, if the environment's unpredictable, then the spacecraft should be able to operate more on their own and be able to do their own prediction, their own planning. So automated planning not only helps science and operations planning, but also enables spacecraft to operate on their own in an unpredictable environment.
For these reasons, automated planning has been used by science and operations planning to figure out what to do and when to do it. And it has been used for autonomously commanding a spacecraft. Planning has been used to figure out how to manipulate solar arrays for the International Space Station. It's even been used for project management for the construction of rockets. So what's challenging about space applications? Scale is one of them. You could have a schedule with tens of thousands of activities, tens of hundreds of state and resource variables. And modeling those states and resources can be complex too. There's a complex interaction between solar arrays and the battery and power availability. Temperature is difficult to model. How would you model a file system? Well, you might be able to model how the spacecraft works, but can you produce schedules that the user really wants? Sometimes the user can't tell you what they want. Also, can you guarantee that every plan that comes out of your planning system is going to be safe to operate and won't crash the spacecraft? So on board the spacecraft, the CPU is about 1,000 times slower than your desktop. I'll briefly describe the history of AI planning in space applications, some of the planners, and their deployments spanning 30 years. In the early 70s, JPL began designing a Mars rover and recognized that the rover would need planning capabilities. That's about the time JPL began research and planning. In the early 1980s, the divisor planner was used for activity planning for the Voyager mission and its encounter with Uranus. Like many of the planners from the 80s and 90s, it was written in the functional programming language Lisp and inherited traits from the non-lim planner, such as partial order planning, subgoaling, and backward chaining. This is done by starting out with the goals at the end of the plan, such as the one at the bottom of the page, and then establishing those goals with the effects from other actions, and then establishing the preconditions of those actions with the effects of other actions, thus building the plan from the initial state to the goals. The new thing the divisor brought was time windows, the reason about metric time, concurrency, in a form of simple temporal constraints, where time points vary within some range and are constrained to be within some range of each other. Clement has been developed as an improvement on Divisor. As you can see, it's been used in a wide variety of applications over the years. One thing that it did differently is it started to model resources explicitly in the language, and it also took a local search approach called heuristic iterative repair. The problem with building up a plan like a partial order is that you can spend a long time trying to figure out the solution and then be left with just a partial plan. The great thing about local search approach is you always have some schedule that you're working with. It may have conflicts and flaws on it, but you're iteratively working on the same schedule. That way you don't have problems with growing memory, and you have a best effort solution, or an anytime solution. A couple of years after Clement was scheduling for the Deep Space Network, the British National Space Center launched a technology improvement satellite project under which the T-Shed scheduler generated a 24-hour plan that was uploaded and executed live on board the Eutelsat-2 satellite.
You'll hear me mix the words planning and scheduling. Scheduling is implicitly a part of planning. Planning is about figuring out what to do. Scheduling is about figuring out when to do it and what resources to use.
The SPIKE scheduler is in use by several missions, most notably the great observatories, like the Hubble Space Telescope. SPIKE takes a different approach than the other planners that we talked about. It represents a scheduling problem as constraint optimization, like a system of equations it needs to solve for. And it has three main stages: a trial assignment, repair where it tries to resolve conflicts among the observations, and then a deconflict stage where it removes the activities or relaxes constraints of some of them. For the Hubble Space Telescope, SPIKE schedules an entire year at the resolution of a minute. That's between 10,000 and 30,000 observations. It needs to use a long horizon because it has constraints which span several months, such as you can't take an observation of the same target within 2 months of another. The Optimum AIV planner was developed by the European Space Agency for the assembly, integration, and verification of vehicle equipment bays for the Ariane 4 rockets. Like SPIKE, it treats the planning problem as a constraint satisfaction problem with resource and temporal constraints. However, its lineage is similar to divisors and planets. The remote agent experiment was the first to demonstrate planning and execution on board a spacecraft. There are three main list components that autonomously operated the Deep Space One mission for 2 days. NASA Ames Research Center is responsible for the planner scheduler and the mode identification and reconfiguration, called Livingston. And JPL developed the Smart Executive. In simulation, it also demonstrated response to unexpected events while on board. This is a common integration of components. The planner scheduler is at the top, the deliberative layer. Underneath is monitoring and execution. And at the bottom is the actual actuators of the hardware or robot. Sensor and state information typically flow up through the layers, and commands flow down.
The Earth Observing 1 spacecraft has been operated by autonomous planning since 2004.
EO1 participates in many sensor networks. Through the Aqua spacecraft is downlinking images as usual, and one of them is detected to have changed since the last time it was imaged by software on the ground. The software signals EO1 to add a high-resolution image goal to its schedule. The autonomous planner reschedules its activities so that it can slew the spacecraft and get the image on its next pass, enabling quicker response to this forest fire. That was Casper on board EO1. This is a continual version of Aspen, JPL's stochastic iterative repair planner. It's the first planner we've talked about that's not written in Lisp, but instead C++. Casper is also part of the autonomous sciencecraft experiment that's on board EO1. This also includes machine learning algorithms that are used for detecting different kinds of phenomena in the images. In this case, it's screening out images that recorded clouds instead of the actual target. Here notices that there's a difference in images, triggering it to take another high-resolution image of the target on which they discover volcanic activity. Aspen has saved the MAM, EO1, and DARPA Orbital Express missions millions of dollars. It's currently being used to schedule ground antennas for the Deep Space Network. Proba-1, the first in a series of several autonomy missions, demonstrated onboard scheduling and resource management. NASA Ames Europa Planner has evolved from the planner scheduler used in the remote agent experiment, now written in C++. Its constraint programming approach to planning and scheduling and As before, it does not differentiate between actions and states, treating them both as variables with temporal extent. Unlike most other planners, its language is object-oriented, which is very convenient for representing large problem domains. It has its own Eclipse-based interactive development environment and is integrated with SPIFFy, a human-centered planning tool that is used by many NASA missions. As part of MapGen, Europa helped the Mars Exploration Rover mission pack more activities into their plans, increasing their efficiency. It has also been used to plan out the movement and orientation of solar arrays for the space station. The European Space Agency MEXAR and RAXIM planners were used for uplink and downlink planning for the Mars Express mission, where they reduced planning effort and increased science return. So what does the future hold for AI planning for space? Well, how about making rovers autonomous? Turns out that the rovers already use AI-style path planning. As you'll see, rover navigation is very sophisticated.
Class, today's lesson is autonomous waypoint navigation in natural terrain. This is your designated goal location. First, watch this video to learn how it's done.
There are ongoing efforts at JPL to make rovers autonomous in different ways. One effort, Aegis, integrates planning, machine learning, and science knowledge. While the rovers do not yet use autonomous planning, other parts of Aegis have been used by MER to autonomously discover and investigate high-value science targets during a long traverse. There are a wide variety of other applications and challenges that require research and planning, like human-robot exploration teams, teleoperated robots, mission and vehicle design, robotic construction of habitats. Other than the rover, there are other kinds of planetary exploration vehicles that need autonomous planning to handle uncertainty brought by weather or ocean currents, like aerobots or hydrobots. Planning is also a part of research in related fields, such as testing, verification, and validation. For example, what are good scenarios to test? What are good test cases? And how should they be ordered to more quickly find bugs or other problems?
Over the past 30 years, AI planning has shown its value in many ways, but still, very few missions actually take advantage of it. There are an unlimited number of applications and opportunities where AI planning can make a big impact. There are many demonstrations of automated planning, but few are operational. In order for AI planning to gain widespread acceptance, we need to make it easier to hand off automated planning systems to the domain experts and take the algorithm experts out of the loop. User interface design is key for solving this problem. Farther in the future, there are many mission concepts that will need capabilities that deployed planners do not have today, including reasoning about uncertainty. There are many areas of planning research that can have great impact on a wide range of applications. I hope you found this information helpful. Thank you for your attention.